Topic 10, Refraction of Light, Part 2, Critical Angle and Total Internal Reflection. This picture might give you a clue as to what total internal reflection and critical angle are. Critical angle and total internal reflection only occur when light goes from optically denser medium, say glass, to a less dense medium, say air. So look at this diagram here. We have a ray of light going from, let's say, glass into air. Here is the angle of incidence, angle of refraction. You can see the angle of refraction is bigger than the angle of incidence because the light speeds up as it goes from glass into the air, and therefore it bends away from the normal. This is the normal here. And as we make the angle of incidence bigger, the corresponding angle of refraction also gets bigger until it gets to a point where the angle of refraction is exactly 90 degrees. That means the ray of light is traveling parallel to the glass face. When that happens, then this angle of incidence has a special name. It's called critical angle. So critical angle is a special case of angle of incidence. And if we make the angle of incidence any bigger than critical angle, like the situation here, then no light will go out into the air. It will all come back in. And this is called total internal reflection. Here it is. We can use the formula for refractive index to calculate the critical angle in a particular medium. In this case, it's glass. And the final answer is the critical angle in glass is 41 degrees to 2 sig fig. To use this formula properly, don't forget, we should call this angle here the angle of incidence. That's the angle of refraction, even though light goes this way, the other way. Now try this on yourself. Find the critical angle in water. Here is another diagram illustrating total internal reflection. The optically less dense medium, in this case, is air, and let's assume this is glass. So when total internal reflection occurs, this glass face behaves like a perfect mirror. There are some practical uses, excuse the spelling, of total internal reflection. First one is optical instrument. Second one is communications technology. Third, medicine. The optical instrument illustrated here is periscope, which consists of two triangular glass prisms. This observer here is looking at this house as the object. A light ray comes in from the house, hits this glass face, and you have to draw a normal to that glass face so you can find out what the angle of incidence is, which is 45 in this case, and it's 45 degrees is bigger than the critical angle of glass, which is 41 degrees. So the light ray gets totally internally reflected back. Nothing goes out. And it goes into this prism, and the process is repeated as it did here, and goes straight out into the observer's eye. You've all heard of optical fibers or fiber optics in communication, like IT. Here we have a piece of this optical fiber, and it's made of. You've all heard of optical fibers or fiber optics in IT communication. Here is a piece of optical fiber which is made up of two types of material, the core and the cladding. Core is optically denser. When a laser beam is shown into the core and hits its face, then you have to do a normal there, and this is the angle of incidence, which will be bigger than the critical angle. So total internal reflection occurs here. And when the beam hits here, same thing happens again, and there again. Eventually, the laser beam leaves the core. So, information can be carried by the light beam down the optical fiber. Here is an endoscope used by the doctor for examining, in this case, the inside of the throat of a patient. This is simply a piece of optical fiber. They shine the light into the scene and comes out the other end, shining at the inside of the throat. And here's a picture of it. The endoscope can go as far down as the stomach, looking at the inside of the stomach.